The next speaker I'd like to invite to the stage is our resident expert on generative design, Erin Bradner. Erin is a distinguished research scientist who leads user experience research here at Autodesk on generative design, and previously has worked at IBM, Boeing, and AT&T. She's also received several patents on advanced design. Welcome, Erin.
Thank you. And thanks, everyone, for joining online. I attended UC San Diego for my undergrad, so a shout out to the Tritons. My first slide is coming shortly. There we go. I've been invited to join the stage today to talk to you about generative design. And when our team here posted the title of this talk, we did get some comments saying, that's new to me. What is that term? I'm going to define it for you and give you some examples today. It's a technology that we've been incubating in the office of the CTO, the technology office, our R&D arm, for the last 3 years. And I'm happy to say that it graduated from the research lab and it is now being commercialized, meaning the technology is being developed for commercial use this year. And I'll show you exactly where that technology is going to live, and you can take a look at that in your free student subscription. Okay, one more slide. So what is generative design? It is CAD, except instead of a designer having fully formed an idea of the design that they want to make in their mind, and then simply transcribing it into a CAD tool, what the designer does, or engineer, is specify their goals. What do I want this thing to do? And the CAD tool, the generative design tool, synthesizes the solution. It synthesizes the geometry. That word synthesize is important here. So with the drone body that you see here, these are multiple different solutions that the generative design tool produced when given simply the gravity load of the battery and the lift of the props. And if it looks like you were seeing something akin to erosion there, that's right. Because what the system does is it initially creates a volume of material. On the first iteration, it removes material. At every subsequent iteration, it does an analysis, a strength analysis to determine how much more material can I remove. Oh, and did I remove too much material? It will add material back. And it will synthesize the form that satisfies your goals and constraints. Those loads, remember the gravity load of the battery and the lift on the props. But since we have recruited infinite computing, we're not going to just solve for one drone body in one material. We can solve for multiple drone bodies in different materials. And as I mentioned, if this term generative design is new for you, you're in good company. This morning, I did a tech trend, a Google search for the term generative design, and as a comparison for topology optimization. So if those of you with mechanical engineering backgrounds will be familiar with the term topology optimization, generative design is trending up. Right, I'm seeing a trend up that term. And I started in 2014. We at Autodesk have been talking about it for about 3 or 4 years. And you see it's trending up. So the idea that we can recruit an algorithm to optimize a form, the difference between topology optimization is I have given the system a seed, a design that I just want to lightweight. I want somehow some help to remove material. And so you would conduct simulation. The algorithm will tell you where you can remove a material. But I had to create that design from my mind. With generative design, the algorithm is synthesizing the solution and not returning simply one optimal solution, but returning a range of solutions. So let's take a look at a simple example. And there we go. Okay, so about last summer, an intern on our team decided she wanted to make a chair. And that was her summer project. She wanted to generate a chair with our generative design algorithm. And to do that, she gave the system the loads of a 250-pound person, maximum load. And she also wanted to limit the creative freedom a bit of the algorithm. So she created a build envelope. That's red. The loads are in green. And she gave the algorithm, I'm going to back up because it jumped a bit farther. If we could back up, that'd be great. She gave the algorithm a set of those constraints and then a range of materials she wanted to work with. And the algorithm produced a number of chairs. She chose this one and fabricated it in wood. Now, it wasn't originally, she hadn't originally had wood in mind, but she liked the look of this solution. So she worked with another, a full-time employee, but who was previously an intern, and she fabricated this in wood. What I like about this is it captures both her design intent, her goals. It is 18 inches off the ground, and it can hold the weight of a 250-pound person. But it also brings in an aesthetic that she hadn't originally thought of. Despite her brilliance, she was a Rhodes Scholar, she would not have been able to produce 100 different chair designs in the 10 weeks she had for her internship. And this chair is, for me, a very emblematic example of generative design. It's algorithms augmenting natural human capacity for design. It is not, in fact, replacing human designers. Here's another example of generative design. And what you see here in the upper right is a car chassis. And that chassis traditionally designed by a team that builds these for stunt cars. So these are welded tubes. What we did is we worked with this team that builds stunt cars for Hollywood. We sensed up this chassis with about 60 sensors, drove it in the desert, and took that data into our generative design algorithm and had it produce a new chassis based on the data. What you see here is the chassis that was formed, synthesized by the algorithm when we said, go ahead and make it in titanium. And does anybody have a full-scale titanium printer that could print a full-scale chassis? No, we couldn't find one. So we said, all right, we can't do that. But what we can do is use chromoly tubes and welding. So we ran the algorithm. We told it, OK, make it out of beams instead of that more organic topology optimization type shape that you saw with the chair. Make it out of beams, and we'll weld it. The design changed, but the performance stayed the same. And the overall weight reduction was considerable. So we called this a hack rod. It was hacked using the sensor data to produce the design. Now, OK, let's back up from an entire chassis and take a look at something simple. So last year, we decided we'd enter a competition to design a engine bracket for GE. And the design on the left removes material through topology optimization, that synthesis mechanism that is going to remove weight until we have one optimal solution. The one on the right takes that design as its seed and removes even more weight by introducing an internal lattice. And what I like about this algorithm is you can almost see it in the image, but the algorithm is not simply introducing a repeating shape for the lattice. What it's doing is mimicking human bone, and it's reinforcing bone, areas of the bone that need to be reinforced based on the load, and it's taking material away from areas that don't receive direct load. So it's not just filling the space with a repeating pattern. And what I find incredibly fascinating is that algorithms like this, it's even called trabecular structure, which is what you call human bone. Algorithms creating trabecular structures are perceived by the human body as weak bone. This is a titanium hip implant, and when the body sees this installed in the body, it is, the body thinks it's weak bone and it grows into it. It's called osseointegration. So this algorithm has mimicked human bone. Now, on my next slide, I'm going to show you a different approach to latticing. What I love about this approach, this is a project that I worked directly with Lawrence Livermore National Labs on. And these beams are 100 micron beams. And what you can't entirely see in this image is that the beam density, again, that thickness of the beam, is varying. It's changing based on where this miniature cantilever receives load. And what's important there is that what I think is in fact exciting is that with one feedstock to a 3D printer, we're able to produce different material behaviors. Because what we gave the algorithm was a different Young's modulus at different locations in the cantilever, and it produced a functional gradient of lattice structures. Now, if my slides would advance, there we go. You can see where the load, it's cantilever, the load is going to be high here. Those struts are thicker. The load is going to be less here, and those struts are not as thick. So the result here is that we're filling in white space in an Ashby chart. We're allowing the algorithm to create bespoke materials, again, with the same feedstock. And these material microarchitectures that Lawrence Livermore is working actively in, it's giving us these bespoke materials. So I'm envisioning a future where, as a designer, I can create a custom material through 3D printing for every product. And not just for every product, but for a gradation within that product. So imagine that I want to 3D print a device that, when heated uniformly, contracts on one side and expands on the other. I can do that if I have the right microarchitecture. So I'm going to tell you about another example. This is a partition. It's a structural partition in an Airbus A320. And it was created with an algorithm. Now, not that topology optimization algorithm or the beam-based algorithm I told you about. This one, the global shape, was designed by slime mold. So, slime mold algorithm. And it would help if I show you how this works. So let me make sure I advance the slide so you can see the algorithm at work. In fact, this is actually the mold at work. OK, so these white spots are food sources. The green is the slime mold growing to a food source. And what that was is the slime mold optimizing for the rail system in Tokyo. That same concept, when put into an algorithm, will help us optimize for the load paths in that cabin partition. And that's exactly what we did. What I love about this approach is that we not only optimize for strength, but we optimized for weight reduction. And what the Airbus team was looking to do was to remove 25% weight reduction. And they got a significant 40% weight reduction. And that approach of multi-objective optimization is something we're going to continue to see more and more of. Multi-objective optimization, strength and weight reduction, strength, weight, perhaps cost, all within one algorithm. There's no single winner when we do this. That was another question we got on Facebook when we posted for this presentation. It is up to the designer to determine which solution is the solution that represents the trade-offs they are willing to accept. For the engineers, it produces a Pareto curve. I pick which solution I'm most interested in. Now, this is the Airbus partition. I just think this is, it's always so funny to see these 3D prints, these magical 3D prints, but this is what it looked like, 112 parts printed in a powder bed of scallum alloy, which is a proprietary material that Airbus owns. Now, prints like this and countless others in metal are limited by bed size. But that's what our applied research lab here at Autodesk is working to do, is to limit the bed size constraints of metal. In which case, my next slide will show you, oh, I moved a bit too fast. Let's see if we can move back. Here's our back. What we can do is print at, put a robotic, there we go, put a robot with a welder at scale printing that chair. Instead of CNC in wood, it's able to print that chair. And what I love about the system is that it's not only depositing the material, so it is also monitoring in real time the deposition to account for the deformation that would occur when the heat is causing a melt pool where they didn't expect it. And it's adjusting the deposition in real time. And it was welding, in fact, that prompted this next technology, which is a commercial product from Autodesk. And this is back to powder bed metal printing. This technology pre-deforms a shape based on its understanding of how a shape printed in metal will deform, so that when you print it, you'll get your net shape. And I'll pause here to explain again that the generative design technology I talked about is not yet commercially available, but soon to be. And the current plan is that it would be included in the NetFab offering, and it would be called Autodesk Generative Design. It is in limited commercial release right now. Now, some of these tools in NetFab, what their purpose in life is to assist in this make stage, right? So you're designing, then you're making. How do I design for manufacturing? I showed you some functionality that will account for the deformation in metals, both large scale and in smaller scale powder bed sintering, laser sintering. We're developing algorithms within the generative design system that will account for your manufacturing method with milling. So if you have a 3-axis mill and you know what end mill, what cutting tool size you want to use, it'll only make shapes that can be produced on that 3-axis mill. If you have a 5-axis mill, then great. We'll give you a shape that has a bit more geometric refinement. Okay, now software is moving beyond optimizing for mechanical performance, and it's starting to understand something infinitely more complex. Now that's the needs of people. So this is our office in Toronto, and I just had last week the good fortune of visiting that office. We used an algorithm to optimize the interior space of that office against multiple objectives. Some of those objectives include adjacency. I want to be by people I work with. It's the kinds of things you think about. Well, I want to have natural lighting, but I don't want to be too hot. I want to be within sort of the thick of things, but I don't want too many distractions. So distractions, views, adjacency, productivity were all things we were optimizing against. And one source of that data was a survey that we gave our users. And again, my slides are not advancing. So if in the back you want to advance my slide, 2 please, 1 more. And the system produced a set of floor plans. It used the hard boundaries of the kitchen and the walls, and it produced not just one, but it produced multiple design alternatives. Hundreds, in fact. And as it planned out the space, it sought to minimize distractions, maximize outside views, and prioritize personal relationships. It did what no human designer could do, which was to exhaustively search the space. Okay, so next slide. So I've shared this example of optimization in architecture, knowing this is a manufacturing group, but to remember that ultimately what we're optimizing for is human-machine interaction. And I share this image of the SpaceX Dragon V2 capsule because I see it as a canonical example of human-machine interaction. We thought it was science fiction, way in the future. It's going to orbit the Earth in 5 short months. Yeah, that's amazing. And the advances we're seeing in manufacturing methods are staggering. So just in the last month alone, in fact, it was the last 3 weeks, Airbus flew its first titanium part. NASA perfected a powder laser sintering method of 2 metal alloys so that it could create a new igniter. And you're all familiar with the sort of 3D printing marvel Invisalign, right? So those dental trays, $1.3 billion in business this year is what's expected. And also, as I was looking at the news, just last month, a low-cost direct-to-consumer competitor of Invisalign just launched. Same approach, 3D printed, but direct to you. So my last slide is something that I just find beautiful and compelling. It's programmable carbon fiber, but it reminds me to think, and this was about 3 years ago, but it reminds me to think and ask myself, what's going to happen when our products don't just sense the world, but they sense, respond, and adapt? And what kind of technologies do we need to develop to account for this new dynamic world that our products are living in? And I think generative design is part of the solution. Thank you.
Thanks so much, Erin. That was a very thought-provoking presentation. See if I can't move forward there. Perfect.